All right, let's talk about recursion. I know, it's one of those topics that can really trip people up in coding interviews. But here's the thing. We're not just going to go over the basics. Today, we're going to uncover the hidden patterns, the secrets that turn these super confusing problems into something you can actually solve, step by step. So let's just jump right in.
Last time we learned what recursion is. Today, we're going to weaponize it. I mean, come on, knowing the textbook definition is fine, but using it to just crush those tough data structures and algorithms problems, that's the real goal. And that's exactly what we're doing today.
You know, the secret to a ton of these recursion problems isn't some crazy high-level computer science theory. Nope, it's actually a really simple pattern. It all comes down to one thing: making a choice. That's it. That's the core idea we're going to break down.
Think of this as your mental model, your North Star. Just for a second, forget all the curly braces and semicolons. Just picture a fork in the road. At every single step of the problem, your code is standing at that fork, and it has to make a decision.
So what's the choice? It's almost always this simple. Do I take this thing or do I leave it? Do I include the current element, whether it's a number, a character, whatever? Do I put it in my answer or do I just skip it and move on? This simple take it or don't take it choice, well, that's the engine for this whole recursion machine.
Okay, theory is great, but let's make this real. We're going to take this take it, don't take it idea and apply it to a classic problem, finding all the subsequences of a string. This is the perfect way to actually see how all these little choices stack up.
So, the problem is this. Print every possible subsequence of the string ABC. And what's a subsequence? It's just any combination of the letters as long as they stay in their original order. So like AC is good, but CA is a no-go because C came after A. Let's see how our simple choice pattern cracks this.
Okay, so we start at the very beginning with the letter A. Right away, our algorithm hits that fork in the road. What are the two paths? Path 1, we take the A, so our current answer is just A. Path 2, we don't take the A. Our answer is still an empty string. Boom! We've just created two parallel universes we need to explore.
And here's where it gets cool. The whole process just repeats. We move on to the next letter, B, and we ask that same question for each of the paths we already have. So that path that had A, it splits again. One branch takes B to become AB, and the other doesn't, staying as A. And what about our empty string path? Same deal. It splits into B and an empty string. See? The possibilities are literally doubling.
And there you have it. Just by applying that one simple rule 2 times, we found every single subsequence for AB. This branching thing we've built, that's a recursion tree. It's basically a map of every single decision our algorithm made along the way.
You can probably see the pattern here, right? Every new character we look at, we double the number of branches. This is exponential growth. So for a string with n characters, you're going to end up with 2 to the power of n subsequences. That's a lot. And that's the price you pay for exploring every single possibility.
So the big takeaway here is the complexity. The time it takes is going to be O of 2 to the n, which, let me tell you, gets slow really, really fast. But the space complexity, that's actually not so bad. It's just O of n, because the deepest our function will ever have to go is the length of the string itself. Okay, so this take it, don't take it pattern is awesome. It's super powerful. But we can level it up. We can make it even better. Let's talk about a concept that has a fancy name, backtracking, but really, it's just like giving our algorithm an undo button.
So backtracking isn't some totally new thing. It's more like an upgrade to what we're already doing. All it means is that after we explore a choice, like we take an element and follow that path all the way down, we then come back and undo that choice. We erase it. Why? So we can then explore the don't take path as if the first choice never happened.
It's really just a simple 3-step dance. You ready? 1, you choose. You add something to your current answer. 2, you explore. You make that recursive call and see where that choice leads you. And 3, this is the magic part, you undo. You remove the thing you just added. This wipes the slate clean so you can go back and explore the other options without your previous choices messing things up.
So, why are we so obsessed with this? Why does it matter? Because this simple little choose, explore, undo loop, it's not just a trick. It is the master key that unlocks a huge number of those really tough coding interview problems. Let's look at how it works in the wild.
Okay, check out this problem. It's a bit of a step up. We've got an array 1, 2, 1 and a target sum of 2. We need to find all the subsequences that add up to exactly 2. See? We're not just finding all of them anymore. We're finding the ones that fit a certain rule.
This is a perfect job for our pattern. We'll still do the whole take it or don't take it thing for each number, but we'll only save the answer if at the very end the sum is exactly 2.
And this is where the light bulb should go off. This is the power of recognizing patterns. That same exact logic, choose, explore, undo, is the fundamental solution to all of these famous, scary-sounding interview problems. Combination sum, and queens, even a Sudoku solver. It doesn't matter if you're placing queens on a board or numbers in a grid. Deep down, you're just making a choice, seeing what happens and undoing it if it's a dead end. You don't need to learn 10 different algorithms, you just need this one powerful pattern.
Okay, so you've got the pattern now. Let's build out your toolkit. I want to give you some real, practical advice on how to spot these problems during an interview, and just as important, how to solve them without stepping on the common landmines.
This is the big one, isn't it? You're sitting in an interview, the pressure is on, they give you a problem. How on earth do you know, aha, this is a recursion and backtracking problem?
Well, you got to look for the trigger words. Listen for phrases like print all possible something, or generate all combinations, or try all paths. Anytime they use the word all, it's a huge red flag. It tells you that there isn't just one right answer. You have to explore that entire decision tree to find every single valid result. That's when you know it's time for our pattern.
And as you're writing the code, please watch out for these common mistakes. The number one error people make is forgetting to undo their choice, forgetting that pop back. If you do that, the choices you made down one path will bleed over and completely ruin the other paths. It's also super important to get your base case right. That's what stops you from recursing forever. And make sure you're not messing with shared variables that could cause chaos in other branches of your tree.
So if you take away just one thing today, let it be this. The goal is not to memorize solutions to hundreds of different problems. That's impossible. The goal is to learn how to see the patterns that connect them. Because once you see the patterns, DSA stops feeling like this random, scary thing. It starts to feel like a puzzle, and you have the master key. You're not just learning recursion, you're learning a new way to think about problems.